Hello. In this video we're going to be discussing Rolle's theorem. So Rolle's theorem says that we have some function f that satisfies three different conditions. One, our function f has to be continuous on some closed interval from a to b. It has to be differentiable on some open interval from a to b. And that the function has to be equal to each other at the endpoints of a and b. If that's true, then we can find some number c contained within this interval such that we're going to have our derivative at that point equal to 0. So it's going to give us some maximum or minimum at that point c. So let's look at a couple of visual examples of this. In my first graph here, I'll have a and b. Remember, they have to equal each other. Their outputs have to equal each other, so they have to be at the same value right here. So this is f of a and f of b both. And so in between these 2 points, maybe my function doesn't do much, and it just stays constant. Well, if it's constant, I can find all of these points that have a derivative. In fact, the whole thing is going to have a derivative of 0. So there's certainly a point somewhere between a and b. Let's say this is c that has the derivative of that point equaling 0. All right, next one. If a is here and b is here, perhaps our function just comes up and then comes back down. Well, if that's the case, then right here at our peak, the derivative of that, the slope of that tangent line is 0. So if this is my c value, then the derivative at that point has a value of 0. In my third example, maybe instead of going up, we go down. Once again, we see we have a valley here, and so the tangent line is going to be horizontal again at this c value. This is an a, and that's a b, poorly written. And so we'll see that f prime of c again is 0. The slope of that tangent line is 0 at that spot. Or it gets a little more intriguing, and it comes up and down and then back. Well, actually then we have two different spots. There's a C1 and a C2. We actually have two different places where the tangent line would be horizontal, and thus two different places where the derivative would be 0. So consider for a moment a ball that's been propelled upward from the ground. If I draw a picture of this, so here's the height of the ball versus the time. And so at 0 seconds, the ball is at a height of 0, thus the f of 0 equals 0 right here. And it's going to end by landing on the ground somewhere where after b seconds of time. And so f of b is equal to 0. And over the course of this ball is going to come up, and it'll peak, and it'll drop to the ground. And so according to Rolle's theorem, there's a moment up in time here that the function has a peak, and it's got a tangent line with a slope of 0. And so what that means is, since we know that our original function was talking about position, our derivative is saying that we have a velocity of 0 feet per second. So we can use Rolle's theorem to do such things like prove that the equation x cubed plus 2x minus 4 has exactly one root. And what I'm going to do is first focus on f of x equals x cubed plus 2x minus 4. And what I know is if I were to plug in f of 1, I'm going to come up with negative 1. And if we plug in negative 2 for x, well, we come up with 8 plus 4 minus 4, which is 8. And so by the intermediate value theorem, we know that since f of 1 is below the x-axis, and f of 2 is well above the x-axis, that to get from one to the other, they had to cross the x-axis somewhere. So we know we definitely have at least one root somewhere between where x is 1 and x is 2. So using Rolle's theorem, how can we show that we have exactly one root? Well, let's actually go through and assume that we have two roots, and we'll say that they are a and b. So x equals a and b, and the result of a and b would make 0. So f of a equals 0, and f of b equals 0. And so x cubed plus 2x minus 4 is a polynomial. It is both continuous and differentiable everywhere. And f of a and f of b are equal to each other. So we've set up 3 criteria for Rolle's theorem. And what this means is that we must have a c such that f prime of c equals 0. That's the conclusion from Rolle's theorem. However, if I were to do f prime of x is equal to 3x squared plus 2. And if I want to try to solve that, so making it equal to 0, x squared is going to equal to negative 2/3. And when I square root both sides, I'm going to come up with 2 imaginary numbers. So there are no reals here. So our assumption that there are 2 roots, an a and a b, must be false. This does not occur because there is no way for us to have a critical value between a and b. So we've essentially proved that there's no max or min, therefore we cannot cross the value or the x-axis twice. And that's information about Rolle's theorem. For now, we are done.